And okay, it's recording. All right, let's go. Thanks a lot.
All right. Well, thanks a lot for having me here. I appreciate the invitation and really happy to be talking about this work. As Emiliano mentioned, I will actually have a chat window open here. So if I say something especially confusing or especially outrageous, something that you just cannot let go by, please feel free to type it into chat and I'll try to keep an eye on it as I'm talking, and I'll try to address it if I can. The work I'm going to be talking about today is actually a very informal summary of a whole line of work that I've been doing with a couple of my students, Tao Yu and Eugene Bagdasaryan. So for all the good parts, credit goes to them. But if I say some nonsense, that's my fault. But also involving many other collaborations, including my host Emiliano, with whom we collaborated on part of this. And yeah, my goal today is to talk a little bit about federated learning, what it is, and why it has very substantial problems, and what to do about these problems. So let's get into it. This picture, I believe, captures the moment when federated learning officially became big. So this is from Google I/O event in 2019, I believe. And you can see here the CEO of Google, a very important person, talking in front of millions of people about federated learning and how federated learning is going to be Google's answer to privacy concerns about Google products and Google data collection. And that was the official blessing of federated learning as an approach to privacy-preserving machine learning, certainly within Google, but also beyond Google, because now federated learning is being pushed by all sorts of major internet companies, including all major AI players like Google itself and Apple, and there are open source alternatives. So anyway, federated learning has really taken off in the past couple of years. And the idea behind federated learning is actually kind of simple and attractive. The idea is this, that the conventional way of doing machine learning is that you collect a ton of data from everybody and you put it into some big cloud or some big server farm in California somewhere, and then you train this massive neural networks on it that have high predictive power and all the good things that follow from that, which raises obvious privacy concerns because it does involve massive data collection, and there are a lot of people who are uncomfortable with the idea of Googles and Apples and Amazons of the world having access to their personal information. Also, in many settings, if we're talking about, for example, financial data or health data, this is not centralized data collection. It's not even a feasible approach because this data is protected by laws, by regulations, and this means that you just cannot give it to these platform companies because they're not authorized to keep it. Plus, for many tasks, for example, a common task in natural language is predictive keyboards, which autocomplete what you type, your searches, your messages, your exchanges. Training data for that consists of things that these companies don't collect and for privacy reasons can never collect. And sometimes it's not even technically feasible to collect, such as, for example, the contents of people's personal messages, like the stuff you type into your chats, into your SMS, into your iMessage. These companies don't collect it, and it would be a huge scandal if they did, because that would enable them to snoop on communications of all of their users. So how do you go about training models in those scenarios? And federated learning is supposed to be an answer to that question. And intuitively, it works by pushing learning to the device. It's a really attractive and simple sounding idea that instead of collecting the data and doing centralized training, you will do training on the endpoints. For simplicity, you can think of the endpoint as being the user's smartphone. And then somehow you will collect models from those smartphones and aggregate them in a way that's going to give you a central model that's as good as you would have gotten if you collected the data. So instead of collecting the data, you just distribute training to the phones and only deal with the resulting models. So why would somebody participate in federated learning? So obviously, when you, like in this world, in the world of federated learning, everything relies on users actually participating in this process. If you go beyond smartphones, if you go to, I don't know, medical or financial setting, you rely on institutions participating in federated learning. And why would they do it? So one reason they do it just because of altruism, because they want to make the world a better place by creating more accurate models. But I would argue that if given a choice whether to participate or not, people actually would need an incentive to participate in federated learning. And the only honestly meaningful incentive that I can think of is that you would participate in federated learning if the model that you get out of this is better than the model you can train on your own. And this reasoning is a little bit implicit in the original federated learning papers, but I think it's actually there because if the model that you get out of federated learning is no better that you can do on your own with your own data without interacting with anyone, you just wouldn't participate. You would just train model on whatever data you got and go with this. So federated learning is actually quite ambitious as an approach to machine learning. And this is already apparent in these early applications of federated learning, such as predictive keyboards, which try to complete people's messages and what they type on their phones. Because unlike centralized learning, where you have the data all in one place, here the data is distributed, and you have to deal with the fact that the data is not distributed identically. In fact, the non-ID nature of the data in federated learning is the #1 requirement in the original federated learning paper. If you look there, when they talk about federated optimization, the #1 property is the fact that the data is not distributed identically across participants. So I have to take that into account. The data is unbalanced, so some users have way more data than others because some people text more, some people take take way more messages. It's massively distributed, so potentially federated learning, which is one reason it's so attractive to Google, is intended to scale to millions of participants. And then there is additional requirements that you want to limit communications because devices are frequently offline or on slow connections. And of course, privacy. That is that you want to train the model without looking at users' private data. That's the core motivation for the whole thing. Because if you didn't care about privacy, you would just collect the data. Here, you do it in a distributed fashion because you care about privacy. So privacy is what drives a lot of technical developments in federated learning, and in addition to the original motivation. So how does it work? I'm not going to bore you with technical details. And by now, there are so many mechanisms and all kinds of aggregation techniques and alternatives and alternative aggregation techniques and so on. But I'll kind of, for those of you who haven't seen it before, which I imagine is not many, I'll kind of try to give you a very high level intuitive picture of how it works. So there are, as always in machine learning, there are multiple iterations of training. And in each iteration, you have the server or the aggregator, as I will occasionally call it. And that aggregator takes whatever is the current federated learning model and distributes it to participants. All participants, if you have, I don't know, dozens or hundreds of them, if you have millions of them, it's going to be a randomly selected subset of participants, so you can select them based on reputation, however you want. Then each participant takes whatever is the current global model and updates it locally by running a few epochs of training on some local data. So that kind of customizes the model a little bit to the participants' local data. And then the resulting model updates are sent back to the server, which proceeds to aggregate them and create a new global model. And then this goes over and over and over again, potentially for thousands of iterations. And gradually, the joint central model that is being trained here by being repeatedly updated on small local data sets of many different participants. The idea is that it kind of gradually incorporates their data into the model, and the central model starts reflecting all the little data sets and all the little tail ends of the distribution of the data that's distributed across multiple participants. But here is problem number one. So it turns out that if you just do it like this, so this is Federated Learning 101, these model updates, they still leak information about users' data. And this is something that original Federated Learning paper doesn't deal with at all. They just say like, oh, we're not collecting data, we're collecting model updates instead of data, so there isn't much leakage there. But it turns out that, of course, from these model updates, because they're the result of training the model on local data for a relatively small number of epochs, by looking at the updates that are shared by participants, you can actually do a pretty good job figuring out what the original underlying data was. And this work on leakage from model updates in Federated Learning is something that Emiliano and his student and my group did a couple of years back, where we basically showed that if you look at gradients that are shared during Federated Learning, you can actually figure out a lot of things about underlying training data. This, of course, should not be surprising, because if you think about this, what are gradients? I mean, like in the standard learning algorithm, I mean, gradients are directly based on training inputs into the model. And when these local data sets of participants are relatively small, of course, gradients are going to leak, because these gradients are directly based on relatively small data sets. But I'll mention just in passing here that this privacy problem that arises because of leaky gradients that are shared during Federated Learning, it's actually a little more substantial than just leaking individual points and training data. Because of course you can do membership inference, which is a standard privacy attack in machine learning, where you can look at the gradients shared by participants and tell if a particular data point was present there. But it goes beyond that, because there are properties of the training data that are being revealed, which are actually uncorrelated with the learning objective. So you can tell if certain people were present in the data set. You can figure out sensitive properties such as authorship of text and various things related to bias. So here is just one little illustration of what's happening there. By watching updates from participants that they share as part of this federated or collaborative learning, you can actually tell when a particular person starts appearing in the data set and then disappears from the data set. So if you think about images, you can see like when somebody trains models based on images, let's say on their phone, you can see that at a certain point of time, just from model updates, you can see that at a certain point of time, a certain person starts appearing in their images, or maybe disappears in their images. And you can imagine you can make a lot of privacy sensitive inferences from that kind of leakage. So just the reason I'm telling you this is to convince you that just sharing model updates instead of sharing data by itself it provides some protection, but by itself, it's not a robust privacy protection. It actually leaks information about data. So there are solutions, of course, to this. One solution that has been pretty actively proposed by some segment of our community is to use cryptography to hide model updates, to aggregate them under encryption through the magic of modern cryptography and secure multi-party computation. So that's pretty good. You can even prove a theorem about this. Say it provably prevents aggregator from inspecting individual models. So that definitely makes the privacy leakage problem better. But does this make federated learning better? And that is actually an interesting question, because it turns out that what this defense does, it takes one problem, privacy, makes it a little better, and in the process of doing this, it makes another problem, which is integrity, significantly worse. And let me come back to this core motivation of federated learning, which is that it's intended for training on non-ID data sets. So the whole idea here is that you have lots of weird users, each with their own little quirky, idiosyncratic, atypical data set, and you want all of their contributions to train an accurate model. So this part is very important because this means that by design, federated learning is going to be deployed in the environments where you have, for lack of a better term, tail users. Called tail users because they're in the tail of the distribution. They are weird. Their data is atypical. Why is this important? This is important because when you do federated learning, you have to worry about users. Since now they have direct influence over the model, you have to worry about users introducing functionality into the model that you didn't want, that's not part of the learning objective. Because after distributing model training to individual devices, you hope that what they're doing is what you ask them to do. That is, they take your model and update it on local data. But there is absolutely nothing in the design of federated learning that prevents a user, one of the users, from doing something else, because you don't know in federated learning what these users are actually doing. You don't know how their model updates are trained, on what data, what they're doing. And this means that any participant in federated learning, instead of doing what the algorithm tells them to do, they can train their own quote unquote model update that contains some malicious functionality or contains, let's say, a backdoor, and insert it into the model. And for many kinds of backdoors, this could even be done without affecting average case model accuracy. So an example of this, maybe we're training, I don't know, an object recognition model jointly, and the model is backdoored in a way so that, for example, a certain kind of object is never recognized. Or if it's an OCR model being trained jointly, I can insert a backdoor that makes sure that it's a great OCR model, except that when it reads my license plate is never decoded correctly. But all the others one are. So the accuracy of that OCR model is great, but there is a backdoor in it that prevents a certain license plate from being recognized, a certain face from being recognized, somebody's comments being classified as toxic. So you can see how this works. And the problem is that it's not clear how exactly to prevent this attack, because it is true that maybe the model update that's being submitted by that participant looks weird, but what is weird, first of all, when you have non-ID distribution, that's unclear. And second, remember I told you about the secure aggregation as a defense against privacy that provably prevents aggregator from inspecting model updates. But if you cannot inspect model updates, how do you even know that some of the participants are not sending model updates that have nothing to do with the original task, but are specifically designed maliciously to change the model so that it contains some additional functionality? So that's a problem. And this attack, by the way, is more powerful. It's than conventional data poisoning. So traditionally in backdoors and so on, they focus on poisoning training data. But here you can do much more because you have direct influence over the model, not via data, but you actually control the local training process. And you can submit model updates that, for example, overpower other participants' model updates, or when averaged with them, produce what you want. So here is just an example of what you can do. For example, you can make certain objects that have a certain feature to be misrecognized, or for text prediction models, for example, you can do a kind of malicious advertising where certain sentences, but only certain sentences, are completed with words of attackers choosing. And this, by the way, unlike conventional backdoors, this doesn't even require the adversary to control the input at inference time. So you can make sure that these backdoors are triggered by the presence of certain objects in the image or by certain features that occur there anyway. And the standard solution to this would be anomaly detection. But again, anomaly detection is very difficult when the data is distributed, when it's non-ID and unbalanced. And furthermore, secure aggregation prevents anomaly detection from being deployed in the first place. So can't really do this. So telling the difference between tail users and malicious users is, as far as I can tell, an unsolved problem. And I would go out on a limb and claim that it's unsolvable, that there is no method that can tell the difference between this is just a user whose distribution of data is a little weird, but still good, versus here is a user who is trying to inject malicious functionality. Just by looking at the model updates, I don't think it's possible to tell the difference. And of course, robust aggregation is another solution that has been proposed. And that's the idea that tries to solve the problem kind of once and for all by discarding contribution of tail users. And there are actually many proposals for robust aggregation out in the literature. Actually, probably a few dozen papers at this point. And their idea is like, okay, all right, I'm not even going to try to distinguish between good tail users and bad tail users. I'm just going to aggregate in a way that makes sure that the result, the model that I have combined from people's updates, doesn't depend too much on any individual's update. It's kind of like a plausible idea. So for example, instead of using mean, instead of using, instead of like averaging things, you just use an alternative aggregation mechanism that's not sensitive to outliers. So you basically aggregate in a way that's robust to outliers. And that sounds okay in terms of preventing attacks. And in fact, it is pretty effective at preventing attacks. But again, it works. The price of it is discarding contribution of tail users. Differential privacy, which is yet another defense that's intended to prevent both privacy attacks for sure, but also, both privacy leakages, but also integrity attacks. It kind of is based on the same intuition. I will train the model in a way that is not sensitive to outliers. That's the whole premise of differential privacy, to compute things that do not depend too much on the presence of or absence of a certain input in the data set. And it has the effect of discarding contributions from tail users. Differential privacy, which I'm not going to be talking about a whole lot today, because presumably you've all kind of heard about this, but differential privacy is a very popular approach these days, which Google is pushing also among other companies. It's a little, if you were ever tried to deploy differential privacy, you would discover all kinds of interesting issues there, such as differential privacy papers. They're very good at proving theorems, but once it comes to concrete values of epsilon, they tend to be extremely murky. And in the context of federated learning, it turns out that to achieve quote unquote reasonable values of epsilons, you need like hundreds of millions of participants. What does epsilon mean in terms of accuracy? It loses accuracy, especially for tail users. It actually has disproportionate effect on tail users instead of reducing their accuracy, which should not be surprising because it suppresses contributions of tail users. It also has various side effects, such as exacerbating unfairness of models. It turns fair models into unfair models, again, because it suppresses contributions from tail users. And it turns out that the privacy protections that it provides, which is the whole raison d'etre, the reason for existence of differential privacy, are also not distributed equally, and it provides much better privacy protection for typical users than for tail users. So, having told you all this, where am I getting with this? Well, here is where I'm getting. Federated learning absolutely needs additional privacy and integrity protections, whether differential privacy, robust aggregation, or secure aggregation, or all of them together. And these are all good techniques, but what they all have in common, they suppress contributions from tail users. This is one thing that I really want you to take away from this talk, is that all privacy and integrity protections in federated learning, they all have this side effect of intentionally or unintentionally suppressing contributions from tail users. So now let me come back to the first question that I used to kind of motivate this whole line of research, why would anybody participate in federated learning? And I claim that the main reason is because the resulting model is better than the model they can train on their own. But here is the thing. That reasoning might work for the original federated learning because it does produce better models. But once you apply differential privacy or robust aggregation or what have you, that reasoning is no longer true. The resulting models lose enough accuracy that for a huge fraction of users, it is no longer the case that they get better accuracy from federated model than they can get by training on their own. And let me be very precise about what I mean by better. If I'm a user participating in federated learning model, for many users, I claim I don't really care how federated learning model performs on some public data set. What I should care about is this. Is the federated model going to be better for me on my data, on my distribution? Is the federated learning model going to be better than the model I can train on my own without talking to anyone? And if the answer to that is no, why would I participate in federated learning? Why would I bother? Because I can train a model on my own data that for my own data is going to be better than a federated model. Why would I even join? And unfortunately, as a result of this privacy and robust aggregation mechanisms, federated learning model is learning is producing models for which, unfortunately, empirically on the individual data of participants, it's no longer true. And this is what I'll call the disparate effect of privacy and robustness, that there is a significant number of users for whom it ends up destroying accuracy for their data. And as a result, they lose incentive to participate. It is actually already true even without any protection mechanisms. If you look at kind of standard word prediction task, which is the main motivating task for the original federated learning, with vanilla aggregation, if you do these experiments, and sorry, the slide doesn't say it, but this was done on the Reddit corpus, which is exactly the same task and same data set as was used in all original federated learning papers. Already for a non-trivial fraction of users, 9% of users without any privacy protections or robustness protections, already 9% of users can train a better model on their own. Once you throw differential privacy into the mix, 20% of users lose incentive to participate. Once you use robust aggregation that uses median instead of mean and is much less sensitive to outliers, for more than half of participants in federated learning, they no longer have any incentive to participate because the resulting model, as a result of robust aggregation, effectively threw away their contribution, and their data is atypical enough that they can train a better model on their own. They don't need federated model because federated model sucks on their data. So they wouldn't participate. And by the way, this is not an artificially non-ID split. I mean, this is based on actual Reddit user posts. So the degree of non-identical distribution, like how different and how atypical different users are, is based on real data. So we didn't manipulate it in any way. They're as atypical as a normal Reddit user would be atypical from an average Reddit user, if such a thing exists. And so that, I claim, is why, okay, so Carsten asked a question on chat. A user doesn't know a priori whether they gain better training. That is a good point. Let me come to it in Q&A, okay? Because that actually requires a discussion, okay? And I promise to come back in this Q&A. But yes, a user doesn't know a priori, so they might participate hoping they're gonna get a better model, but I'll address this later. But empirically, more than half of them are not gonna get a better model than they can train on their own. So let me go out on a limb here and make an aggressive claim here, okay, just to rise you guys up. Usually when you have a choice between accuracy, privacy, and robustness, you kind of have this unpleasant choice where you get 2 out of 3. Like, for example, with secure aggregation, you get great privacy and maybe accuracy or robustness. But if we're talking about tail accuracy, I'm claiming it's actually 1 out of 3. Okay, so you really, you can get privacy, but then you don't get accuracy and you don't get robustness. Okay, there is a flood of questions on chat. Some of them I do want to address right now, so I'll do this. Which users tend to do better off with a local model? Users who have, it's actually interesting, we talk about this at length in the paper, and we have like experiments for this. So users who have lots of data do better, users who have atypical data do better, and there is a little bit of a barbell distribution. So please look in the paper because we do have a bunch of experiments to address exactly at that point. What we mean training by their own, that's exactly what we mean. They're only training on the data that they would produce model updates from, so on their local data set. Where local training is better, how valuable is that user's data in improving the FL model? That is a very great and subtle question. It is helpful for improving accuracy of the model for other users, but not enough to make it more helpful for the local user, but it does help other users. And then there is a question about private set intersection from John, which is a great question, and I'll postpone that to Q&A. But you guys are asking exactly the right question. Like maybe my data, like it doesn't make it really better for me, but it helps other users, and it does. And what is the nature of the data on which it doesn't work very well? That is an important question, and we discuss it at length, and I'll talk about this later. But let me tell, I don't want to run out of time. So the trade-off I'm showing here is basically saying that if you're an atypical user, you're kind of screwed, okay? Because you're not getting things better from federated learning. So what should be done, right? So what should you do if you have a suspicion that your data, you're not going to benefit from the resulting model in the presence of privacy and robust aggregation? And this is where we come to the salvaging part. So what should you do? And our solution is going to be deceptively simple, or maybe not deceptively simple. So it turns out that there are simple techniques that actually really help. And we're going to start just like we're doing in federated learning. That is, we're going to aggregate model updates in whatever way and distribute them to participants. But at this point, it turns out that it is extremely helpful for participants to take the global model that was distributed to them and then do local adaptation. That is, take that central inaccurate model and adapt it locally. Now, I'm sacrificing something very important that federated learning is doing, because the whole idea of federated learning is that I'm going to take these local models and I'm going to build one good federated model to rule them all. What I'm doing here is saying, okay, let's not now worry about getting one accurate model, because that accurate model cannot be accurate for everyone. Instead, let's take that one central model, possibly inaccurate, and use it to create 1 million local models, each of which is going to be empirically accurate for that particular user. So I'm effectively going to use that federated learning model as a starting point. And there is a question from Martin here, other mechanisms to trade loss of privacy for increased benefit. Again, that's a very deep and important question, and I'm sorry to say this, I will postpone it until Q&A because that's a longer discussion, okay? But here, maybe, if all I'm interested in is local accuracy, I can have my cake and eat it too. That is, I can get high empirical local accuracy and still contribute my data in a centralized model. And this will really take advantage of this something that we discussed on chat right here, that somebody asked. I don't remember who. Might have been, oh, it was also Martin, who said this, because like this process of taking a central model and then adapting it locally will allow me to take advantage of other participants' data. So there is still a fact that like other participants' data improves my local model, but by doing local adaptation, I will actually make it better than the model I can train on my own. So I still get the benefit of other people's data, and I still get the benefit of privacy and robustness, and I still get a good local model. So what do I mean? So the big idea here is that instead of a single and accurate model, we're going to get lots of individual models, including individual models for tail users. So no longer one central model. And now participants have incentive to participate, because it turns out that the adapted model is actually better than the central model on their data. And the central model, yes, of course, we're producing it using private and robust federated techniques, because the need for private and robust federated aggregation didn't go away. Because if I don't use like differential privacy, then updates are going to leak. And if I don't use robustness, then of course somebody could introduce a backdoor. So of course I'm adapting a differentially private or robust central model, or both. As the case might be, although these mechanisms don't play very well with each other. So yes, so I'm adapting this private robust model, and I'm adapting it locally. Which techniques? So we investigated a whole bunch of techniques. Some of them have been used for personalization of models before, fine-tuning, but we also used other techniques like multitask learning, which is actually a little fiddly in this scenario, because in multitask learning, you have to do it carefully, because effectively, it's almost like you have the global task that the central model is using, and the local task, which is adaptation on local data. And unless you do it carelessly, you end up effectively training the model on local data and forgetting what the global model has learned, which is equivalent to discarding contributions from other users. That'll be equivalent to just learning on local data. And then another technique that we tried is knowledge distillation, which is again a known technique, but as far as I know, it hasn't been used in this adaptation scenario. And which of these is better is kind of a multifaceted discussion, because depending on the scenario and depending on the distribution, some of them dominate others. So we produced a lot of charts out of this with no conclusive answer. But one important lesson from this is that adapted models are more accurate for individual users than federated model, for sure. And for a huge percentage of users, it's actually more accurate than the local model that they can train on their own. And so with adaptation, they actually now have an incentive to participate, because they're going to get back a federated model, which is going to make, which they can then adapt and outperform their local model. But in terms of which technique dominates, it's tricky, because if your local, it depends on whether your local model is accurate or not to start with, because if it wasn't accurate, some techniques give you better improvement. It depends on what aggregation mechanism is used. There is no kind of simple single answer to this. Importantly, there is a huge improvement for tail users, because tail users were exactly the ones who were getting hosed by private and robust aggregation before, and they get the biggest benefit from local adaptation. But the good news, sorry, I skipped too far. So, but the good news is that even non-local users, they still benefit from adaptation as well. If a user chooses to keep quiet while others are actively participating, can they still benefit from federated model? Maybe, maybe not. That depends on how federated learning is deployed. There are so many scenarios for federated deployment now that there is no single answer to that question. In the original Google vision, yes, they benefit, because it trains a word prediction model that gets deployed to every Android phone, so everybody benefits. Actually, it is already deployed, from what I understand, in Gboard, so everybody benefits. But for other applications of federated learning, I don't know, biomedical, which is always given as a kind of good case for federated learning, there presumably you don't get anything if you don't participate. So that depends on the environment. All right, I now want to go into the discussion, but before I do this, here are the main takeaways that I want you to take away from this talk. I claim, and again, that's a bold claim I'm making, but and this is not a theory, this is an intuition, that to achieve privacy and robustness, you must bound the influence of outliers. And if you bound the influence of outliers, the central model will not be accurate for tail participants. The second thing that follows from this, and I'll call it a conjecture because I don't have a proof of this, but in a single federated model, you will not be able to balance privacy, robustness, and accuracy. Something will have to give. Like if you're achieving privacy and robustness, you will not have tail accuracy. If you have tail accuracy, I will be able to inject a backdoor into your model. If you prevent, or it will leak some information about some tail participants' training data. If this conjecture is true, then we will not be able to solve these problems with a single model. And one simple way to deal with this, instead of a single model, lots of models. Local adaptation seems to work well. There are several promising adaptation techniques, but I feel that there is a lot to be done here. There could be hierarchical adaptation techniques. Maybe you can cluster users by similarities. Maybe, as John suggested there, maybe you could run some secure protocols like SMC protocols to figure out like users that are similar to you, and then you together join kind of as a subcluster, you join a federated model just for you guys, and you're different from the rest of the distribution. I mean, I feel like there is a whole field of research here, which we barely started exploring, but I do want you to believe that there is this trade-off there that needs to be solved and cannot be solved in a single model. A draft of our paper is online. It's called Salvaging Federated Learning by Local Adaptation. It's a little bit stale. We have been working on this for almost a year by now, but we haven't updated the draft. But I think you'll kind of find the main ideas and a lot of experiments in that archive report that's out there. So anyhow, I think that's pretty much what I wanted to talk about. So let me show up again on screen here, and I'm happy to answer questions. And I know I postponed some questions until Q&A, so I can start with those, or people are welcome to ask their own.
Okay, I'm going to stop the recording then now.
Okay, thank you.
Thanks.